Welcome. Today we are going to discuss the celestial object which after the sun is the most prominent object in the sky. This is the moon. So, the moon, this picture shows you the moon, and the moon is known to have a mass of 7.3 10 to the power 22 kilos. Compare this with the mass of the earth, which is 5.9 into 10 to the power 24 kilos. So, this is roughly 100 times smaller, maybe a little less than 100, of that order though. Whereas, look at the radius of the moon, it is 1700 kilometers, and the earth is 6300 kilometers. So, the radius is around 5 times, little less than 5 times smaller, 4 and something. Okay. So, the mass is considerably smaller, but the radius is 1/4 roughly of the order of size of the order of 1/4 smaller than that of the earth. So, this gives you a rough idea of the mass and the dimension of the moon. The moon we know is in orbit around the earth, and here we know that these orbits are going to be ellipses, we have learned. So, these orbits also will be governed by Kepler's laws. The same the orbit of the moon around the earth, again you can treat as a test particle moving in the fixed gravitational field of the earth. It is an ellipse with the earth at the focus. So, let us just look at some of the orbital parameters. So, the average distance from earth is 384,000 kilometers. It is 0.0025 astronomical units, 26 astronomical units. So, it is pretty small compared to the distance from earth to and between the earth and the sun. This is a kind of insignificant fraction of the distance between the earth and the sun. And the perigee, which is the distance of closest approach, is 363,000 kilometers. The eccentricity again is quite small, it is 0.05. So, it is nearly a circular orbit. The variations in the distance are not very large. It is a nearly circular orbit, the orbit of the moon around the earth, which is why we see the moon more or less subtends a fixed angle in the sky. If the moon were to move further away and come closer, sometimes you would see the moon very large and sometimes you would see it extremely small, but that is not the situation. Now, the sidereal, the orbit of the moon is inclined by a small angle 5 degrees, 5.1415 degrees to the orbit in which, to the plane in which the earth moves around the sun, that is the ecliptic. So, the moon is nearly, the orbit of the moon around the earth is nearly coplanar with the orbit of the earth around the sun. There is a small angle 5 degree, and the direction of rotation of the moon around the earth coincides with that of the earth around the sun. So, the angular velocities point in the same direction, and if you, the moon itself rotates around its own axis, if you consider that, then the sidereal orbit period, this is the period after which the fixed distance stars come back to themselves. This orbital period is 27.3 earth days, but this orbital period is okay. So, the or sidereal, sorry, the sidereal, that's the sidereal orbit period, and the sidereal rotation period of the moon is the same. So, as a consequence of this, we always see a same surface of the moon. As the moon rotates, it takes the same time to go around one rotation as it takes to complete one orbit. As a consequence of this, we always see the same side of the moon, and we do not know, we do not directly see from earth the dark side of the moon, the side which is away from us. Okay, so that is a very interesting thing. And the orbit of the moon, the axis of the moon's rotation is inclined at a small angle of around 7 degrees to the orbital plane. So, the rotation axis is inclined at a small angle around 7 degrees to the orbital plane. So, these are some facts about the lunar orbit around the earth. Okay. Now, the origin of the moon, where did the moon come from? Was it formed when the solar system formed? Was it a fragment that condensed separately around the earth? Well, it is believed that the moon was formed by the impact of an object, of another astronomical object with the earth. So, maybe an object of the mass of, with the mass of Mars. Such an object collided with the earth, and in this collision there was material ejected, and that material formed the moon. That is what is currently believed. So, that is the current picture of how the moon was formed. Now, when you look at the moon in the sky, you see that there are different phases of the moon. Sometimes you see the moon very bright, and sometimes you only see a part of the moon illuminated, and sometimes you do not see the moon at all. So, we have the full moon, you have the crescent moon, you have the new moon where you do not see the moon at all. Okay, so, these are the different phases of the moon, and this picture shows you why you have the phases of the moon. So, the sun is in this direction, and the earth, we are here on the earth. This is the relative position of the moon. When the moon is in the direction of the sun, then the moon will be overhead in daytime, and only the back surface of the moon, the surface that is away from us, will be illuminated. So, we do not see any illuminated surface of the moon. This is the new moon. Okay. And then the moon in its orbit moves like this. So, when it moves here, we start seeing a part of the illuminated surface, and you have the crescent moon, and then you start seeing half the illuminated surface. You have this is the first quarter of the moon, and then here you start seeing a larger part of the illuminated surface, and here you see the entire illuminated surface. The moon is exactly away from the direction of the sun, and then again you have so this is the waxing moon and this is the waning moon. It comes back all the way over here. In India we call this the Shukla Paksha and the Krishna Paksha, when the moon is getting when the size of the moon increases, and then when it decreases. So, you have this cycle where you have the different phases of the moon, and this defines a month. The lunar cycle defines a month roughly, okay. And the synodic month, which is the time period between when the phases of the moon repeat, is slightly larger. It is 29.53 days, whereas the sidereal lunar orbit is 27.32 days. Now, this is very easy to understand. This is the sun, and this is the earth, and this is the moon. So, let us just consider this position and ask so this is the orbital period. The orbital period is the time it takes for it to go around and come back to the same position. But you have to bear in mind that the earth also is moving. So, when the earth is here, the moon will then, in one orbital period, the moon, one sidereal orbital period, the moon will come back to the same position which is parallel to this. Okay, parallel. So, I have not drawn it exactly parallel to this. That is in one period, that is in 27 0.32 days. The moon will come back to exactly the same position, but you see it is no longer at the same angle relative to the sun. So, to come to the same angle relative to the sun, it has to cover still some more angle, it will take some more time. Okay. The picture is possibly clearer if I draw it like this. This is the sun, earth, and the moon is here in a straight line. So, we have a full moon and when the earth has moved here, then this is one orbital period of the moon, but for a full moon it has to come here. So, this is one orbital period, it has to come cover this extra angle, which is this angle here, for the full moon to occur again. So, it will take a little more time, which is why these two periods are different. Okay. The actual period varies slightly, this is because of various perturbations on the moon's orbit. Okay. So, these are average numbers. Now, the moon and the sun both subtend around half a degree on the sky, which is a very useful thing to remember. The moon and the sun both subtend around half a degree on the sky. So, if you can extend your fingers and block just the sun or the moon, safer to do it with the moon, you know that this angle which your finger is subtending at your eye is half a degree. Okay. So, that is a fixed angle on the sky. Another interesting consequence of this is that since both of them subtend the same angle, you can have eclipses where one of them blocks the other. Okay. So, so you have eclipses, and you can have both kind of eclipses, lunar eclipses and solar eclipses. So, in the lunar eclipse, the shadow of the earth falls on the moon and you do not see it, and in a solar eclipse the moon comes in between the earth and the sun and you do not see the sun. So, this shows you a picture of a total solar eclipse which occurred in 1999. You see here the sun is completely blocked out by the moon. Now, if the earth and if the earth's orbit around the sun and the moon's orbit around the earth were coplanar, they were in the same plane, then you would have an eclipse every time the moon came to this position. It would precisely block the sun, and you would have a solar eclipse every time the moon came to this position, and you would have a lunar eclipse every time the moon came here. The earth's shadow would fall on the moon, but you do not have eclipses once a month, they are not so frequent. Why is this? Why do not you have eclipses every month, two eclipses every month, a solar eclipse and a lunar eclipse? This is because the moon's orbit around the earth is inclined at a small angle of 5 degrees relative to earth's orbit around the sun. So, eclipses only occur when the moon's orbit cuts the ecliptic. See, the sun and the moon have to be in the same position. So, let me just draw these. On the sky, the sun moves around in the ecliptic, which looks like this, and the moon moves in an angle which is inclined. So, this is the line joining these two, the moon's orbit and the sun's orbit, and eclipses can occur only when the sun is located here or here. If the sun were located here, there is no way the moon could intersect, come in front of the sun. Okay. So, eclipses occur in two parts of the sky where the moon's orbit cuts the ecliptic plane. Okay, the word ecliptic comes from there actually. And so they can occur twice a year roughly. There are 2 times in the year when you can have eclipses, and you have approximately 4 to 7 eclipses every year. Now most of these eclipses are insignificant, they are not a very spectacular thing to see, because the overlap may be very small. Total eclipses are quite rare, they do not occur all that frequently. Okay, for a total eclipse you need the moon and the sun to be exactly coincident, but eclipses can occur whenever the sun is in this region and there will be some overlap between the angle subtended by the moon and the sun. So this again shows you the picture of the total solar eclipse. Now with this let us move on to something slightly different, which again is closely related to the moon. This picture over here shows you a place called Fundy Bay. Now just look at, it's the same place, these are 2 pictures of the same place at different times of the day. So this is, in this picture you see there is water filling this entire region, and in this region, this picture you see that this region is entirely dry, quite dry, the water has drained out, and this occurs maybe once or twice every day. There is a beach called Chandipur very near, around 100 kilometers from here in Orissa, where again you have quite a spectacular thing. The sea recedes around 3 kilometers and then again it comes back. So you go there in the beach, and if you go there at some time you will find there is no water at all, and other times you will find that there is water all around. So this is the phenomena of tides. So the water level in the sea, it comes up, goes up and down over some period of time. This is the phenomena of tides. So that is the topic that we are going to discuss next. And so there are different kinds of tides, okay, different types of tides which vary from place to place and time of the year. So let me show you a picture which illustrates the different kinds of tides you can have. This picture, on the x axis you have the time, and along the y axis you have the sea level at some place measured at some point. So this period is the time period of the tidal period, it is called the tidal period, it is a period after which the tide repeats, okay. And this period from here to here is 1 day, it is a tidal day from here to here. So these are called the this is called the semi-diurnal tide. So you see you have 2 high tides in 1 day. 1 day is from here to here, okay, and in where you have places where you have semi-diurnal tide, you have 2 high tides with interspersed with low tides in a day. You also have the possibility of diurnal tides. Here you only have a single high tide in a day, this again is a day, and the tidal period is the full day, 24 hours roughly. Here the tidal period is 12 hours, of the order of 12 hours, semi-diurnal. The other possibility is a mixed tide. In the mixed tide, the tide, you have a high tide and a low tide every 12 hours, but one of the high tide is larger and the one in between is smaller, again you have a large high tide and a small high tide, okay, it is a mixed tide, mixture of diurnal and semi-diurnal. Now the question is, what causes the tides? So, to understand what causes the tides, let us take up for discussion the following situation, where we have a massive object over here of let us say mass m, and consider 3 test particles. So, we have one test particle over here, let us call this another test particle here and other test particle here. So, let us call these A, B and C, and these are all falling freely in the gravitational field of this massive object of mass m located here. And let us say that the distance to B is r, and A and B are at a distance small r relative to B. Okay. So, that is the situation that we are considering, and let us write down the so let us now consider an observer who is sitting on B and ask the question, what is the acceleration that this observer will see for A? Okay. So, the quantity we are interested in is d square r dt square for A. Okay. D square r A dt square, that is the acceleration of A relative to an observer sitting at B. Okay. Now, it is obvious that A is going to experience a gravitational acceleration that is more than that of B. So, A is going to experience an acceleration that is relatively away from B towards this massive object, because A's acceleration, A being closer, A's acceleration is more than that of B. So, the relative acceleration between these two particles is the g m by r plus r A square minus g m by r square. That is the relative acceleration of A with respect to B. Right, sitting on B, that is what I will see, the acceleration of A to B. It will move away from B because it is experiencing a larger acceleration compared to B downwards. So, now let us take this term, this we can write as g m by r square 1 plus okay, and this assuming that this separation r is much smaller than the distance of these 3 objects from the massive object, we can do a Taylor series expansion, and if I do a Taylor series expansion, then I will have of this term, then I will have sorry, this should be minus here, not plus, because the distance here is smaller, so this should be minus and not plus. So if I do a Taylor series expansion of this, I will have one more term which is now 1 plus 2 gm into Ra by R cube. That is it. So this cancels out with this, and we are led to the equation that okay. Now if you repeat the same exercise for the particle C with respect to B, if you repeat the same exercise with the particle C with respect to B, you will then see that C experiences an acceleration which is less compared to B. So B is being attracted here with some acceleration, C experiences an acceleration which is smaller. So if I sit on B, I will see that this point C is moving away in this direction. Okay. So the same thing can also be written for the point C. I will have exactly the same thing. So the bottom line of this calculation, if you repeat it, will be that if this is the observer B, he will see both A and C accelerating away. So these, he will see that they are both accelerating away with an acceleration which is equal to 2 gm by r cube, where r cube is the distance to the massive object into r. They are both accelerating away. Okay. So that is the relative acceleration between these two. Let us now consider the same thing. So let us consider the same problem again, where I have a very massive object of mass m over here, and there is a test particle over here called B, sorry. Let us now consider A and C to be in these directions, in the transverse directions, instead of being in the radial direction. Okay. So now let us draw the acceleration of B. The acceleration of B is in this direction, whereas the acceleration of A is again towards the center of this mass, it is in this direction. C is in this direction. Okay. To do this analysis, it is most convenient to introduce vectors. So let me introduce a coordinate system. The coordinate system we are going to use is like this. Let us call this the x axis, let us call this the y axis. So we introduce a coordinate system like this, and let us write the equation, the vector equation for the separation between this and this, the relative acceleration. So I am sitting at B and I ask the question, what is the relative acceleration of the point A, of the test particle A. I am accelerating with the test particle B. So let us write that. So d square r A dt square is equal to so the acceleration of A, acceleration of this test particle A is equal to, so it is pointing, you can see from here it is pointing along minus x and minus y both, the acceleration of this. So this will be equal to minus gm by r square. Now we are assuming that this distance is much smaller than this distance is capital R, and ignoring second order terms. So if you ignore terms of this order, if you ignore terms of order r by r squared, then this distance is the same as this distance. If you ignore terms of this order, second order, which is what we will do, okay, because you apply Pythagoras theorem, this is equal, this distance is this distance square plus this distance square, the square root. So if you ignore the square term, then this is just the same, so as this, so gm by r square, and the direction in which it points is it has a component along the x axis which is I, and it has a small component along the y axis, and that small component of the y axis along the y axis you can see is essentially 1 plus r by r j. That is the direction in which this vector points. So that is the acceleration of the test particle A, and I have to subtract out the acceleration of the test particle B, so that will be plus gm by r square into I. That is the acceleration of the point B. So this gives me the relative acceleration between A and B. So if I sit on B and ask what is the acceleration of A, I get this, okay. So this tells me that d square r A dt square is equal to minus g m by r cube into r A. So the bottom line of this calculation is that if this is the observer B falling, and these are the two test particles A and C, they are all falling in the gravitational field of this very massive object. So the relative acceleration between A and B is pointing inwards, that you can see from here, the relative acceleration is inwards towards B. Similarly C will also accelerate relatively towards B, okay. So and the magnitude of the acceleration is gm into the separation by r cube. So this is, these accelerations are what are referred to as tidal accelerations, tidal forces. These forces and acceleration are what are referred to as tidal forces. So this picture basically summarizes the effect of tidal forces. So consider a ring of objects like this falling freely in the gravitational field of a massive object located below, at some large distance below. So the very massive object is located at some large distance below this, quite some distance away below this, okay. All of them are falling freely in the gravitational field of that massive object. Now if I sit at the center, if I fall freely, if I am sitting on the object which is at the center and ask what is the relative acceleration between me and these other objects, I will find that objects located radially with respect to the massive object are all accelerating away, and the acceleration is proportional to the separation from me, which is r, and it is proportional to the inversely proportional to the cube of the distance from the very massive object. Okay, and you have this factor of 2 times the gravitational constant into the mass of the very massive object far away. If you look at the same thing in the transverse direction, the relative acceleration is inwards, and the dependence on these r and capital R remain the same, just a difference of factor of 2 between this and this. Okay. So, these are the tidal forces, and these tidal forces are extremely important, and the tides that we see on the change in the level of the sea that we observe on earth is a consequence of these tidal forces. Okay. So, let us now next estimate which of these astronomical objects, the two nearest nearby large the two dominant astronomical objects in the sky, which of these cause a greater tidal acceleration on the earth? Is it the sun or the moon? So, let us just make an estimate of this. To get put these numbers in perspective, the acceleration on the surface of the earth produced by the earth itself, that is g, is of the order of 10 meters per second squared. Right, we know this. Now, let us first calculate the acceleration of the sun on the earth. So, the acceleration of any object on another, gravitational acceleration, is g m by r squared. So, sun on earth, and to calculate this, so we have to take the gravitational constant, which is 6.67 10 to the power minus 11, we are working in SI units, and the mass of the sun, which is 2 into 10 to the power 30 kilos, and divided by the square of the distance, earth sun distance, which is 1.5 into 10 to the power 11 meters. So, if you put in these numbers and calculate this, this turns out to be 6 into 10 to the power minus 3 meters per second square. It is a insignificant fraction of the acceleration of the earth on an object at its surface. Okay. Let us do the same calculation for moon. So, if you do the same thing with the moon again, so we have 6.6 into 10 to the power minus 11, and then the mass of the moon we have just seen is 7 into 10 to the power 22 kilos, much smaller than the mass of the sun, and the distance also is much smaller. The earth moon distance is the distance is 3.8 into 10 to the power 8 meters. So, the distance is also smaller, but and the mass is also smaller, but the fall in the mass is extremely small, is quite large. So, it results in an acceleration which is many times smaller than that of the sun on the earth. So, if you look at the acceleration of the earth, the moon produces a negligible effect compared to the sun. Okay. Now, let us calculate the thing that we started out. So, let us look at the tidal force, tidal acceleration. So, let us look at the tidal acceleration. So, to calculate the tidal acceleration sun on earth, we have to, so tidal acceleration is given by gm r by r cube, or essentially what you have to do is you have to calculate gm by r square, which we have already calculated, and then here you have to put the radius of the earth. The earth is falling freely in the gravitational field of the sun. So consider an object, consider the center of mass of the earth at the center of the earth, and ask what is the relative acceleration between the surface and the center of the earth. So the distance between the center and the surface of the earth is the radius of the earth, and this has to be divided by the earth sun distance. The radius of the earth we know is around 6000 kilometers. So this this ratio, the r to r ratio, the radius of the earth and the earth sun distance, this ratio comes out to be 2.6 into 10 to the 4.5 into 10 to the power minus 5 meters, 5, and the tidal acceleration then has a value which is 2.6 into 10 to the power minus 7 meters per second squared. So the distance, the earth sun, the ratio of the earth's radius to the earth sun distance is very small, 10 to the power minus 5. In contrast, if you look at the moon on earth, the tidal force acceleration of the moon on the earth, the earth moon distance is relatively not that small. The this ratio comes out to be 0.02. So you see, even though the acceleration of the sun on the earth is much larger than the acceleration of the moon on the earth, the tidal acceleration produced by the moon is larger than the tidal acceleration produced by the earth, by the sun. It is roughly twice, little more than twice. So when you are looking at the tidal acceleration, it is the moon which makes the dominant contribution. Okay, that is the first point we have to remember. Now look at this picture again. The moon remains fixed, let us say, in this along downwards direction, below, somewhere below here. The earth is rotating. Okay, so let us come to that later. So the moon is fixed below, and you have these kind of relative accelerations between different parts of the earth. The center of mass of the earth is falling freely in the gravitational field of the moon, and there is a relative acceleration which tends to, what if the earth were an elastic object, which it is to some extent, this relative acceleration would produce a deformation of the earth like this. It would be compressed, it is compressed along the direction perpendicular to the moon, transverse to the moon, and it is elongated in the direction radial to the moon. Okay, this effect is actually there. Now this is if it were a solid, but the surface of the earth to a large extent, 75% of it is covered by water. So under the influence of such accelerations, the water flows, and the water will tend to flow in this direction, in the direction which of elongation. The water will flow over there, and the water will flow out of the regions transverse in the transverse direction. Now this whole thing is rotating. The earth rotates every 24 hours. So if you are sitting at a fixed place on earth, you will experience an elongation every 12 hours, once here and once here. You will express a compression every 12 hours, once here and once here. Okay, so this is what causes the tides. The water flows in response to these accelerations. Now that is the dominant component, the moon. The sun also produces a component which is slightly lower, smaller. okay, roughly half. So both these things together produce the tides. So let us look at what causes the tides. The main component is referred to as the principal lunar semi-diurnal component, okay, and this has a 12-hour 25 minutes period. This has a slightly longer than the 12-hour due to the lunar orbit because of the rotation of the moon around the revolution of the moon around the earth is in the same direction as the earth's spin. There are other effects also which modulate the tide. You have sun's gravity, then you have the inclination of the earth, and moon's orbit varies, etc., okay, various other things. It also depends on the topography, the geography of the coastline. So the study of tides in itself is a very detailed thing which we shall not go into. Our main interest here is to understand how it arises and its relation to the tidal forces. Okay. Tides are roughly classified into, I mean, you refer to them as spring tide and neap tides. These are important things. So you have a spring tide. The spring tide occurs when the sun and the moon are aligned. So this occurs either during a new moon or during a full moon, and when the sun and moon and the earth are in a same straight line, this is called syzygy, SYZ. So when this occurs, the tidal acceleration of the sun and the moon, they reinforce each other, they add up, they are in the same direction, the elongation occurs in the same direction. So the tidal forces, you have pretty strong tides, and this is called a spring tide because the water springs up, the water level really jumps up, okay, that is why it is called a spring tide. And you have a neap tide when the moon is in this position or this position. So when you have the first quarter moon or the third quarter moon, here the tidal acceleration of the sun and the moon, they are opposite. So the moon will cause an elongation in this direction, but the sun will cause an elongation in this direction. So they will cancel each other, so you have relatively low tides, and again you will have a spring tide when the moon, when you have full moon. Okay. So that is that I have briefly told you about what causes the tides in the sea on the earth. Tidal effects are quite ubiquitous and they are very interesting. So let me now briefly discuss another tidal effect, and this is called tidal disruption. So consider a situation where I have a very massive object, as astronomical object, let us say of mass capital M, and I have another object which is of a smaller mass, small m, and the distance between them let us call again capital R, and the radius of this small object is R. Now let us assume that the small object is a gravitationally bound object. So this small object is itself gravitationally bound, it is held together by its own gravity. So for example, I could have a galaxy, this is a galaxy and this is a very bigger galaxy, much bigger galaxy. So there is a small galaxy, some small astronomical object which is gravitationally bound together by its own gravitational acceleration in the neighborhood of a much larger gravitational object. So let us now see, consider this possibility, the tidal force, tidal acceleration of this object on this is going to try to pull this apart. The tidal acceleration of this very massive object on this is going to try to pull it apart. This is true whether it be gravitationally bound or not. Suppose I take you and take an object and put it in the neighborhood of a black hole, very massive object. When this, as it falls into the black hole, the gravitational tidal effect of the black hole is going to try to pull these different parts of the object apart, and it is going to try, it is going to compress it in this direction. Okay. Now, if the acceleration pulling it apart is larger than the forces that, so the forces that are pulling it apart are larger than the forces that are holding it together, this is going to get disrupted, it is going to break. Okay. So, this is the thing which is referred to as tidal disruption. So, let us now ask the question, under what condition is a gravitationally bound object. So, this is a gravitationally bound object, under what condition is it going to be disrupted. Okay, this is a very important thing. So, the relative acceleration between the center and this surface, this test particle here is 2 g m by r cube into r. So, that is the acceleration that is trying to due to the force that is trying to pull it apart. So, the upper surface is moving away from the center with this acceleration. Now, let us calculate the force, the acceleration due to the force that is holding it together. So, it is held together by its own gravity, and its own gravity produces an acceleration g into m, the mass of this small object, by r squared. So, if we want to find out under what condition these two become exactly equal. So, this is the condition under which these two become exactly equal. Okay. So, let us see at what distance from this massive object will another object get disrupted. So, that distance turns out to be r cube is equal to 2, then I have the ratio of these two masses into r cube, or this is called the tidal radius. For this object. Okay. And if this object comes closer than this distance, let us call it RT. Okay. If this object approaches this bigger object closer than this tidal radius, it is going to get disrupted. And this kind of disruption is a common phenomena in astrophysics. You have what is called galaxy cannibalism. So, in the center of big clusters of galaxies are region where you have many galaxies in a compact region, you find that there are extremely large galaxies. These extremely large galaxies grow by the process of galaxy cannibalism. So, what happens is, if a smaller galaxy comes within its vicinity, if it comes closer than the tidal radius, that smaller galaxy will get disrupted, and the debris that is produced is then again fed, eaten up, it goes into the larger galaxy, and the larger galaxy keeps on growing by this process. So, tidal interactions are very important in astrophysics. So, today we have seen, so today we first calculated what this tidal acceleration is, tidal effects are, and then we saw two very important, one very important on earth, that is the tides in the sea, and second we also discussed the tidal disruption of astrophysical objects, one astrophysical object by another. So, let me stop today's lecture over here. Yeah.